Welcome to the third and final lecture of this lecture series that I'm giving on Tetryonics. So today we are finally going to see the 3D time domain model of these quanta. We're going to talk about time dilation, general relativity, conduction, longitudinal electromagnetic waves, how we can connect all of this to math, as well as entanglement, and finally the inverse squared relationship for electric fields. So before, we said that these quanta oscillate, that they're quantum inductive loops. They have positive and negative electric field components, one on either side, and a corresponding north-south magnetic dipole on one side and a south-north dipole on the other. So we know, once again, from Maxwell's equations, that a changing electric field will produce a magnetic field, and that a changing magnetic field will produce an electric field. So the way that we describe these quanta in time, as this picture here is essentially a time average of all these different field components over one period of this quanta, is we simply rotate them around its central axis to get a surface of revolution in three-dimensional space. And this gives us our three-dimensional quanta. So here we have a positive quanta. Now once again, this is Maxwell's equations, where a curling magnetic field, which is these arrows here, will produce a conduction current and what is known as a displacement current. In this case, since we're talking about free electromagnetic waves, this conduction current is zero. We don't have any moving electrons or protons. We also know that a curling electric field is going to produce a changing magnetic field. So here we have this net electric field vector pointing forward. And we say that this electric field is changing in time because it's moving. So it's moving through space. So this is the result of a plot that I've done of how we could essentially have, it's almost like a magnetic field vortex that goes around and it gets smaller and smaller and smaller, and how this can be used to create an electric field. So we have this isn't really a simulation, it's just a plot. And then we take the curl of it. And then what we get is electric field lines. It's hard to see, but it's traveling around a helix, around a cone. So we have this curling electric field creates a time-varying magnetic field. A curling magnetic field creates a time-varying electric field. They're time-varying because it's moving through space. So what ends up happening is because our electric field is traveling around a helix, around a cone, this magnetic field actually points up in some directions, like this, and it points down in others. So we get this sort of like sawtooth sort of direction around the cone. And this has a net sort of like tangential vector going that way. So this is very similar to our two-dimensional quanta, where we saw that the magnetic field goes up at an angle during going out during one direction and in at an angle the opposite direction. And we said this doesn't contribute to the net motion of the geometry, and once again we see that it's more of a symbolic description, and this is associated with the tangential velocity, so that these quanta twist basically like a corkscrew. So this is what a chem field would look like in 3 dimensions, where once again we have forward velocity components and backward velocity components and multiple charge components. So once again, it behaves the exact same way as the two-dimensional one, where it has a net forward velocity equal to the number of rows. This is our two-dimensional velocity. It's the chem field essentially just viewed from above, perpendicular to the plane that these cones are located in. Now, because these quanta have different magnetic twists associated with them, if we essentially look at the back of the chem field here, what we have is that these internal twists cancel. If we look at this, oops, that's the wrong way. If we look at this geometry, we know that these quanta, these electric fields, have to twist in different directions in order to create their corresponding magnetic fields due to the left-hand and right-hand rules. So we say that a positive quanta obeys the right-hand rule. If we curl our right hand, or our fingers curl in the direction of the magnetic field, our thumb points in the direction of the electric field. If we curl our left hand, we get our fingers curling in the direction of the magnetic field and our thumb pointing in the direction of the electric field. So the electric field, the net electric field, points vertically up because it goes along a corkscrew, essentially, or like a helical corkscrew. And then the electric field is going to essentially twist the opposite direction. But when we view these from the back, what ends up happening is that they all twist in the exact same direction, even though they are different charge components, because they're oriented differently in three-dimensional space, we get the same twist. So these twists internally cancel, and what we're left with is a net force couple going around the outside. So what ends up happening is this is going to cause this entire chem field to now rotate clockwise, or counterclockwise, viewed from the front, because it's obeying the right-hand rule, because on its outer edge it has positive quanta. So what this allows us to do, something that I'm currently investigating more, is we can abstract essentially all different possible measurements in physics to transformations upon discrete geometries. So we can have velocity, which is obviously meters per second. We can say that these geometries are moving in time. This can also describe momentum. It can describe force when they overlap and create an acceleration or a change in the energy content of these geometries. We can rotate, or we can revolve them about a central axis and describe angular momentum, as well as the charge in the magnetic field. Because what we can see now is that this charge is essentially directly related to a specific direction of twist. So we can twist in one way or the other and have positive or negative charge. And this also has a corresponding magnetic field polarity. So we can rotate, and this can describe time. So we can have a repetitive rotation, and we can say each period is one tick of a clock. This can describe quantized angular momentum, as well as, once again, it's related to charge and magnetic field polarity. We can expand these geometries as they move through space in order to describe Doppler independent redshift, which we saw yesterday. We can shrink them to once again describe Doppler independent blue shift, which is going to become important at the end of this lecture when we talk about entanglement, and electromagnetic wavelength contraction. We can also add and subtract these discrete geometries into a larger one in order to describe work, mass, and energy. So this essentially creates an idea that, once again, I'm still working with, that in physics, we have algebraic symmetry as a result of geometric symmetry. That essentially there is no difference between describing physics in terms of geometry and in terms of math. It's the exact same system, just a different way of looking at it. So once again, a positive quanta obeys the right-hand rule. We curl our right hand, our fingers travel in the direction of the magnetic velocity or the magnetic field, and our thumb points in the direction of the linear velocity and the electric field. Negative quanta obey the left-hand rule, so we curl our left hand to get the magnetic velocity and the electric velocity. So these are different sizes, not because they actually are, as I just once again cropped the picture in a different way. So what is very interesting is that before we saw that a chem field has no net charge because if we flip it over, we see the opposite field components. In 3 dimensions, what happens is we say that these quanta technically don't have a net charge by themselves because if we reflect it through itself, we now have a twist in the opposite direction. So if we view them from the front, we get one twist. If we view them from the back, we get a different twist. But they still have always a net forward velocity in a specific direction. So what this allows us to do is it actually allows us to describe reflection. So if we have one chem field moving up, and now it interacts with another one in such a way that it can push this quanta back through itself, this quanta will then move down one, and it will overlap with its own chem field. So we know that all of the upward-facing quanta have a velocity going up, and all of the downward ones have a velocity going down. So we can see that when we flip one of these quanta over, it's going to overlap in such a way as to accelerate itself back through the chem field. And as it does so, it's actually going to flip polarity. Now this is very significant because we know that when we simulate electromagnetic waves with Maxwell's equations, but when we have a reflection, the electric field shifts polarity and the magnetic field remains the same. So that's basically what Tetryonics is describing, is that the geometry has been reflected back through itself. In order to create a reflection, we require that the amount of forward velocity associated with the tip quanta is overcome. So we know that for every row in a geometry, we have one forward velocity. So we need at least two to overcome this one. But we have an additional condition where it has to take up the exact same area as one. So this is the whole idea that we'll see later. We can have essentially describe this geometry as having one smaller quanta for every one of these cells, or we could say that this is actually 4 for every cell. So we have 4 quanta take up as much area as one, and it overlaps. We can overpower it and push it back through itself. Since we can connect the cycling of this geometry to time dilation, we'll also see that we also have to have a phase match between these interacting geometries. So we saw a chem field rotates in time. Force is created by overlap. In time domain, we require overlap in space as well as time. So they have to overlap in the same plane when they interact in order to achieve maximum force. Otherwise, they don't. So we also require that not only does 4 quanta take up as much area as 1 in the more higher energy density geometry, but that there is at least one complete phase match as they move over this distance, the distance from the base of this quanta to its tip. So once again, we can, every time we see a two-dimensional geometry in Tetryonics, we can essentially think of it as a revolving door and revolve it around its central axis to get the resulting three-dimensional geometry. So these are electrostatic fields. This would be a positive electrostatic field. So we saw before that there is a magnetic zipper that holds these two things together and keeps them from just breaking apart. So here we see that takes the form in 3 dimensions as twists in opposite direction. So once again, we come up with this idea that this technically doesn't have any field polarity information. What it has is information about tessellation. And the way that we can see how this is sort of held together is if we look at our right hand as we curl it, and so we try to look at the opposite side by walking in a circle to see the curl in the opposite direction, we can't do it. So essentially every left-handed curl has a right-handed curl over top of it on the opposite side. So all we see is the exterior left-handed curl. So once again, this is the geometry for a magnetic field as well as a photon. And if we rotate it, we get this, where we have this positive field and this negative field. And once again, we can see that we have the other possibility for the way that these twists can superposition, and that is that here they reinforce each other, going in the same direction. So once again, we said before that photons, as they propagate, in general, they expand, and that was because they had an enhanced admittance component. So we can also think of it as sort of a centrifugal acceleration, that as it spins, it throws the energy outward. So once again, the two-dimensional geometry is essentially a frequency domain analysis. So they're drawn as being a static geometry, but they're not. So this is a simplified version of the three-dimensional system. And now we can also imagine how quantized angular momentum is kind of an area per second. Because if we look from a reference plane at this geometry as it rotates at this plane, we're going to see the most area here. But if this geometry is at an angle to our reference plane, we see less total area from within our reference plane. So we have this changing area per second as it rotates. So what is interesting is that we can essentially perform math using simple geometric relationships as well as this one frequency component for every 2 quanta in order to calculate how big these quanta actually, or how big these geometries actually are in terms of their energy. So what I've done here is I've used this whole, we have two quanta for every one frequency component. And then I've equated this with the idea that we have E equals HF, quantum mechanics tells us the energy of a photon based upon its frequency. And we can calculate the number of quanta across this geometry as a result of energy. And then we can relate this to the wavelength, because we said that each one of these diamond geometries is one wavelength. So we can multiply them together to get the length across this geometry, which we see here. So we can also do this for a bunch of other different geometric properties. So we can calculate the width of a photon, which I said was from one point of the diamond to the opposite one. We can describe the side length, which is all the same because it's equilateral, the total area, the area per quanta, and the side length of these quanta. We can perform all of the exact same calculations for chem fields as well. Later on in the lecture, we're going to once again see that the wavelength of a photon is not anywhere close to its actual size. It is much, much bigger. Now, the reason, once again, we have a periodic geometry through space, and as it moves, it creates periodicity through time as it moves past a point. So we have described quantized angular momentum as essentially being a projection of area like this into this reference plane. So I'm not entirely convinced that that is a good way of describing it. I think Kelvin has actually made an error in the way that he has described quantized angular momentum, and that what we should really describe it as a mass flux. So we're talking about, once again, just kilogram meter squared per second passing through a reference plane. Because what we're going to see is that, once again, a high energy content is going to shrink. So we think it should have less area, as well as move more slowly because of time dilation. So once again, if we want to prove that a high energy content geometry rotates slower, we can go back to this idea that we have a constant force couple. Now this force couple is constant no matter how much energy this geometry contains. It's always just going to be one this way and one that way. So we have a lot of quanta in here and a lot of mass. We can kind of think about this in terms of a mechanical system. If we push on something with a constant force, but it has an increasing amount of mass, we will make it travel slower and slower as it gains more mass because it has a lot of inertia. But we also know that these geometries' wavelength contract. So we're left with this weird there's sort of two things that are going on here, where if we have a small radius and say a constant angular velocity, this should rotate faster. We should get a net number of complete rotations than if we had a larger radius. So what really matters is the rate at which the velocity changes with respect to energy compared to the rate at which this radius changes with respect to energy. So we can have one essentially overpower the other. And that we're still going to get a slower rotation for a smaller radius, even though because we have essentially a slower velocity still than in this condition. So a large geometry will actually rotate really fast, and a small will rotate slow. So the way that we do that is we essentially just apply Newtonian mechanics to these quanta, which we say that we can do because energy is fractal and all the big systems behave the exact same way as the small systems. So essentially we have the centripetal acceleration is a product of mass and the tangential velocity squared over the radius. So we can solve for the tangential velocity. We can use this relationship that I showed before where we can calculate for the side length of, say, a photon or a chem field, where here we're specifically doing a chem field. And we can get this. So we can substitute that into our original equation, and then we can transform this tangential velocity into a angular frequency by dividing by the radius. Once again, just using classical Newtonian mechanics. And we get this equation. And if we simplify that, we get this very interesting and amazing result, that the frequency is inversely proportional to the energy content. So what this essentially tells us, and that we're going to later connect to general relativity, is that space and time, the way that we normally think of them, don't actually exist. Space and time have no measurable properties. We can only measure things relative to each other, say if they're opposites or different energy content and rates. So here I've calculated what these different angular frequencies are based on this assumed force. Now this assumed force I got from a paper where they say that this is the smallest force that has ever been measured. Because it's the smallest force that has ever been measured, it's not necessarily one quanta of force, because it's very unlikely that you could actually measure a single quanta of force. So this force is probably a huge, absolutely huge overestimate. And what we do is we can calculate for different common energies of visible light, where this is, I think this, which one is this? This one is visible red, this is like green. And then once again we see that, or no, this, yeah, this should be red. So we have essentially a higher angular frequency than for the green one, it is lower. So this is on the order of microseconds. Now this gives us a very, very important relationship that we're going to talk about a lot in the second half of this lecture, that the frequency components of a photon are not equal to this angular acceleration or rotation of this chem field. I mean, they might be. It depends upon what we should actually use for that centripetal acceleration. So it's not entirely clear. But in general, for right now, we say these are not the same thing. Quantized angular momentum is completely different from the frequency, say, of a wave, as we're going to see later. Now, with regards to waves, we're going to talk about this now, but it'll be more important later. So we can see that they have a certain polarization. So we have a net separation of positive charge down here that, say, points up to this, because electric fields typically point from positive to negative. Then we have a north magnetic field component on this side, which will point to the south, which goes that way. And once again, we know that this thing is rotating, and that force is created by overlap. So if we overlap a certain geometry, let's say a charge field with a photon polarized this way, depending upon the polarity of that charge field, it's going to be accelerated in a certain direction, and we'll create a change in energy, and then that will correspond to some kind of measurement. So we'll measure the polarity of this photon in time, depending on how much overlap we have. But we'll see here that we can only get positive out of this for a certain measuring electrostatic charge polarity. And what we're going to see later is that, say, an electromagnetic wave is comprised of frequency components that have been polarized in opposite directions. In terms of the magnetic field polarity, what happens is that if we look at this geometry going in from the side, where we essentially see the edge of this chem field, we would get essentially the maximum amount of magnetic velocity that we could get. So that's sort of like the maximum phase of the magnetic field. So we can once again see that we're going to change between how much positive electric field we have and, say, north or south magnetic, or positive electric field we have and north or south magnetic field we have, depending upon how this geometry overlaps into our reference plane as it propagates. And we're going to get this essentially changing electromagnetic wave. Now once again, we can relate these differences in rotational velocity to general relativity. So once again, general relativity describes gravity as a gradient in energy density, and we also say that it curves space and time. That when we have a high energy density, space compresses about it, and time dilates and progresses more slowly compared to out here. Whereas if we have a low energy density, space expands. Points are more distant, and time progresses faster compared to in here. So this is normally depicted like this. where we can actually have, say, a planet curve space and time and make space more dense over here than out here. And this is essentially describing like a gravitational potential well. Tetryonics says, no, this is what happens. It says the energy is compressed close to a region of high energy density. That's why it has high energy density. Once again, we saw before this due to them all overlapping and essentially compressing each other inward. And we have just shown that if it has a high energy content, this geometry is going to rotate slower. As it travels outward, the energy will expand, and as it gets bigger, we'll essentially have less energy content per area, and now this quanta will actually cycle faster. So here we have a dense amount of space that, say, energy occupies, and here a low one. So we can think of that as actual spatial coordinates. Let's say if we were trying to measure these geometries like we saw in the first lecture where we feel one geometry with the other, we're going to get more points over a shorter distance here than out here. We're also going to get more complete ticks or less complete ticks of a clock in here because it cycles slower than out here. We're going to get more ticks. So this leads to a bunch of different very interesting things that don't necessarily seem to be related immediately, and that is that Laplace's equation is actually a law now. It has to be true all the time, and it can never be broken. So Laplace's equation describes the divergence of some quantity. So this is commonly seen when we're modeling, say, something like the heat equation, how heat will propagate through a metal plate. And if we touch something really hot to something cold, the heat is going to conduct through it and eventually spread out and become equal everywhere. Now, the reason why this happens is actually because of time dilation. So we said that force is created by an overlap. In 3 dimensions, it's overlap in space and in time. Geometries with a low energy density spin faster. So we can kind of imagine that if we had a whole bunch of geometries all interacting, the ones that have the least energy content, excuse me, the ones that have the least energy content, they will get more overlaps per second, and they'll essentially win the energy race and eat up all of the energy before anything else can. So we get this condition where energy can only flow from high density to low. Nothing else is possible. We also, this is not entirely related, this is kind of an aside, but we also have this question now that once we have a 3-dimensional geometry for chem fields, and say this is a plane of cones and it's rotating, if we average where all the energy is through time, what we get is another bigger cone. So we're left with the question, what are these cones made out of? As far as I can tell so far, they're made out of smaller cones. And the way that we can see this is through this change of variable. Before I said to get reflection, we need 4 quanta to take up as much energy as 1 in one of the interacting geometries. And we can have this happen due to wavelength contraction. So what we can do is we can say, let's reparameterize one of these quanta to instead be 4. And what we'll find is that all of our mathematical relationships and restrictions on this geometry still work. We're still going to get a total square number, as we can basically prove down here. We're still going to have it equal to all the incremental odd numbers of this square number summed, or the number of rows squared. And we get all of the same results. So we get this weird idea that in Tetryonics, quanta technically don't exist. We can talk about as small as an energy increment as we want. Correspondingly, as large as a time measurement as we want, like a very, very slow tick, because when we have a small amount of energy, it cycles slower. So using this idea, we also can arrive at this result where we say the uncertainty principle is actually a law. And like we saw before, it actually has absolutely nothing to do with randomness. It's an intrinsic property of these geometries. In order to do that, we kind of have to reinterpret what these differentials mean. So in the case of energy, we say it is literally an any energy differential. if we have a very, very small increment of energy, say per area, we correspondingly have many, many ticks per second. So this delta t, we shouldn't call it a time interval. We should call it the number of ticks per second, like the number of full clock cycles. Correspondingly, if we have a very slow number of ticks, we have very large increments of energy, where say we have transformed 1 to equal 4 or something like that. Now we also have this uncertainty relationship where we say if the geometry is very spread out, then we have small amounts of momentum associated with it across its area. Of course, we can also say the opposite, that if we have a lot of momentum, which is very dense, then we have a very short wavelength. And once again, we get this idea that the uncertainty principle is actually more restrictive in Tetryonics than it is in the standard model. This can potentially also lead to a gigantic amount of confusion when we're trying to apply math to things. So we end up with this idea that we have real or measurable space, imaginary space, measurable time, imaginary time, and many different measures of frequency. So in terms of measurable space, we know that force is created by overlap. We essentially have to feel one geometry with another. Because these geometries are subject to wavelength contraction and the uncertainty law, there's essentially this, we can't measure space to essentially an arbitrary precision. We're limited by what is essentially the size mismatch between these geometries. So we once again end up with the idea of quantization of quantum systems and the idea that we can only describe them in most cases in terms of statistics, if we're talking about like a real application, like if we're actually going to calculate this or build this device, we have to rely on statistics and probability. So, but then we have imaginary space where technically math is only constrained by our imagination. So even though we can't measure space continuously, it still exists continuously because space has no properties, it's just empty. We also know that these geometries can continuously overlap. And so what ends up happening is that we're only going to have quantized energy and changes in force. But once again, just because we haven't measured a change in energy yet doesn't mean that things aren't interacting in some way on the quantum level. So we'll once again have measurable time, where once again this is what we can actually measure in the laboratory and what we can practically work with. And then we have imaginary time, which is like imaginary space, where we say things don't stop existing just because we're not interacting with them. If we leave the room, the chairs in this room don't suddenly disappear because we're not looking at them. They're still there, they still have properties. So, and frequency, we're going to see, is kind of odd. We can have frequency as the number of discrete units moving past a point. We can have it as this intrinsic cycling of energy. And yeah, we can also have like a composite frequency where if we're bouncing a ball, obviously we can bounce it so fast and stuff like that. So now we're going to talk about conduction. And the process of conduction are going to eventually be related to entanglement. So in Tetryonics, a voltage is described as a separation of charge. Now this geometry doesn't actually exist. This is kind of just a theoretical thing that is helpful to wrap our head around it. What would really happen is we have two different electrostatic field geometries that have been overlapped, but they are held apart from reuniting by some kind of force. So this creates potential energy. So this potential energy is, since it's constrained from reuniting right here, if we give it an easier path to flow through, it will expand through that path and reach equilibrium. Just like one of our very first assumptions, energy is going to expand to its minimum density and seek equilibrium. So there are multiple methods through which this energy can be transferred through this external circuit and create electrical conduction. The first, that everyone is probably the most familiar with, is the actual physical motion of charge. So we say that positive and negative charges, well it's mostly only electrons practically, will actually carry this energy inside of their chem field through the external circuit. One that might not be familiar with people that we're going to eventually relate to the entanglement is that we have something known as displacement current, where a photon is a discrete packet of electromagnetic radiation that oscillates and it moves through space, but it can also move through materials. So inside of a circuit, if we have some kind of alternating current source, we will actually have electromagnetic waves traveling through the circuit at the speed of light. And this is what displacement current is. Now, these electric and magnetic fields can superposition in such a way to create a standing wave, and in many cases the standing wave basically already exists inside of the material, that the energy can pass through this standing wave almost like it's a vibration or a bunch of pulses. So this is the start of what we call longitudinal electromagnetic waves in Tetryonics. A longitudinal wave is a wave that moves in and out. So we can think of it like a pressure wave. Like if I clap my hands, that is a pressure wave. It's partially comprised out of longitudinal components as well as transverse components. So transverse is up and down or maybe side to side, and a pressure wave is in and out. We can also call it a longitudinal wave. Another example is an explosion or a shock wave. So what happens in some materials is that even when they're at their rest energies, the chem fields of electrons, this little yellow thing here, can already be overlapping. And say if this is a proton. So what ends up happening is that the energy can basically just hop from one chem field to another without causing any displacement of the electrical charge. It's like skipping a rock across a pond. And that basically looks like this. So it goes that way. Obviously, this is a very idealized situation to simplify the explanation. And once again, we can see why through mu. Mu is like an admittance. We know that for a certain amount of energy, it's going to want to expand. It doesn't like being compressed. It wants to expand and reach its minimum density and reach equilibrium. So what this tells us is that for the most part, actually physically moving electrical charges is a waste of energy. We don't actually need to do it in order to transfer the energy. This helps explain superconduction. I'm actually going to go back one slide. So when these chem fields overlap, we can think of that charge field as, once again, cycling, because all these fields have this intrinsic omega that causes them to cycle. When it overlaps, we can transfer energy into one of the electrons' chem field, and we essentially get a pulse. So even DC can be described as pulses that occur very, very, very rapidly. So fast that we basically can't measure it. The way that an electron becomes part of conduction current is it just happens to be in a high enough energy state that the pulse can knock it free of its location in an atom, and it becomes conduction current. So generally we know that if we increase the temperature of a conductor, the resistance goes up because we're causing more conduction current, and the electrons, as they move, they bounce around, they lose the energy in their chem field to just random motion inside of the material, and this results in losses. If we supercool a conductor, well, what ends up happening is that basically none of the electrons at some point are in a high enough energy state to be knocked free when the pulse comes. So that's what superconduction is. Now, superconductors typically you don't measure a magnetic field about them. And the reason why is, once again, the magnetic field of conductors is created by the chem field of the electrons moving through them. The superposition of all of these chem fields creates the magnetic field. So when we talk about a solenoid, what we've done is we've put a whole bunch of loops very close to each other. And so we have electrons traveling in opposite directions, essentially at the same point when we're looking in from the outside. So we have one chem field pointing that way, another pointing the opposite way. So they're traveling two different directions, but they're on two different sides of the coil. So what we see is this net superposition that creates this magnetic field typically associated with solenoids. So in terms of transferring the energy, we basically don't want conduction current to occur. In terms of getting useful work out of the energy, we need conduction current in order to create these magnetic fields to cause essentially electric motors to move and things like that. Or if we want to heat something, we want to waste as much energy as possible in terms of heating the material. Now, we're left with the question, how do these fields superposition? The answer is that it's not very clear. So if we're lucky enough, we might have this result where if we perfectly overlap them, it's going to already equal a square number, the sum of the two square numbers that are interacting. But that barely ever happens. But what we could do is we could say, let's convert these into a sum of squares. We want the minimum amount that is possible in order to conserve energy, so that we essentially get this condition where we have one very large chem field and one very small, and we say let's just ignore the small one. That's essentially the best solution I've come up with so far. But then we have this problem, well, what if we have 9 plus 4? What happens then? I don't really know. We can also have them superposition at an angle, where we say we have 5 rows going that way, 5 rows going that way. And for here, I'm just going to guess that these are at 45 degrees to make this simpler. And we can decompose them into essentially x and y components like we're familiar doing with forces. So we have 3 going that way and 3 going down in terms of this 5-row one. And then we have 3 going that way in terms of the 3-row one. And we just add them back together and recompose it into a single geometry. So we can get the result that we have one geometry that has 3 and one that has 4 going in different directions. And we can recompose that once again into some kind of downward facing one. But we're once again left with the same problem that this doesn't necessarily conserve energy. It doesn't even entirely make sense. But it's an estimation that we can essentially work with so far and maybe even experimentally validate. In some ways, this actually does kind of make sense because if the energy content of these chem fields is quantized, if they overlap and there isn't enough energy to actually create a change in energy of the other one, we can essentially say that no interaction is going to result. We don't transfer the energy because it doesn't have the minimum amount to add at least one row from one chem field into the other one. So once again, exactly how we can relate the superposition to the net result of this solenoid or other systems is kind of unknown. It's a work in progress. Now we can also describe capacitors, where once again we said that a voltage is overlapped electrostatic fields that are being held apart even though they want to come together, or say they could be wanting to repel, but they're held together. So we talked about in the previous day that this is due to the polar nature of the molecules inside is how we can essentially store energy, almost like a spring, where we displace them from their preferred bond orientation. And this creates essentially potential energy. Now what is interesting in Tetryonics is that we can immediately see that capacitors, in order to maintain this potential energy, actually have to consume power. This is very, very odd, but you can kind of think of it like if you're holding a spring compressed, eventually your hand is going to get tired from holding it compressed. You could hold a spring compressed with essentially an immovable object, but eventually what is going to occur is that the spring is going to get tired, or it's going to permanently deform, and then there's no longer any potential energy. So essentially we say that capacitors actually consume power. They don't actually just store potential energy perfectly or indefinitely, which we know that they don't. If you have a capacitor that's charged and just leave it for long enough, it might take hundreds of years, but eventually all the energy is going to go away. Now, something that is very interesting that people have probably noticed and have noticed for a long time is that the differential equations that describe a spring mass damper system are exactly the same for an RLC circuit, but we have changed which constants we're using in front of these derivatives. So this is for electrical circuits. We have the change in current to the second derivative in terms of time first, and then none. And it's equal to some kind of function, like we're inputting energy into this system. So we saw before that mu, essentially, it's like an admittance or some kind of momentum that when we have energy, it wants to expand. It wants to keep going in the direction that it's going. We saw that epsilon is like springiness. So we can kind of guess that if we wanted to actually model these three-dimensional quanta in time, which is once again something that I'm currently working on, we can potentially do it with a differential equation like this, where we say mu is like L and epsilon is like C. The part that is difficult is that then we're left with, well, what is this mass term? It seems like the mass term should actually still be mass. It should just be energy, which is very confusing to work with because it means that energy, to a certain extent, is a tautology. It essentially exists because it exists, and it has properties because it has properties. So it's something that is not easy to model or create a mathematical equation where you can actually say, okay, we say that force is the result of overlap. How exactly do these quanta jump from one geometry to another to create an acceleration? That's something that is unknown. We just apply the conservation of energy and just say that it has to. But in terms of the actual time description of it, we don't yet have that. Now, what is interesting about differential equations is that one of the solutions is an exponential function, that we get a rate of change that is proportional to itself. This is very interesting because conceptually that is very like our triangle. It has a very, very large energy and it grows and decreases in odd numbered jumps. It's going to change at a rate that is proportional to its own magnitude. We can also see here that if we put it in a specific position, it approximates the exponential because part of the exponential is basically linear. Now we're going to show that, well, we're not really going to show it, but we're going to see that we can describe normal graphs that we're familiar with in mathematics and physics as being the result of a bunch of different chem field amplitudes where we're looking at them at the edge. So you might be familiar with the concept of an integral where we slice a graph into different sections with different amplitudes. Essentially, we can say that we can put a triangle of a certain amplitude at a bunch of different points along this exponential in order to create the exponential. And what ends up happening is that we're going to show that time dilation results in the curviness of graphs. And we're going to explain this through examining the process of emission in a little bit more detail. So this is the way that an electromagnetic wave is normally thought to look like in the standard model. We have, say, negative electric field components, positive electric field components, a north field, I think that's what that's supposed to be, and then the south field. And that it creates essentially an oscillation between these different components in time and in space as it moves through space. So this isn't necessarily actually a part of Tetryonics because in this lecture we're seeing a bunch of things that I've created that Kelvin doesn't necessarily agree with. He doesn't think that three-dimensional quanta can describe matter the way it should be, but I think it makes it work better because we can see how there is some kind of standing wave component to the geometries and why if we touch fascia, we're going to create this force that is dependent upon a phase match. So what I'm saying is that we can essentially describe an electromagnetic wave, which is comprised of many photons, as photons of opposite polarity. So this is very weird and very different from the normal interpretation of Maxwell's equations, where we say that this creates the negative electric field component as it moves through space and time. But I'm essentially saying no, this electromagnetic field is a result of a bunch of different Gaussian pulses with different polarizations. And that when we measure the frequency of a wave, we're measuring the frequency of the source, not the individual frequency components of the photons. So this is a more simplified version of how we can describe emission, because we saw before that an electron spins and it stores energy in its tangential velocity. Here, if we have a charge in simple harmonic motion, it can bounce between these two different boundaries and say, at one instant here it's going to have zero velocity and then it's going to be accelerated downward. And as it starts its acceleration, it's going to have a minimum velocity As it passes through the center, it'll have a maximum, and then eventually it will deaccelerate to a minimum velocity down here and then go back. So we can essentially say that these different polarized photons are emitted from the maximum velocity going in different directions. So we can have one polarization associated with this maximum velocity and the other associated with that one. Or once again, we've seen before, when a chem field reflects, it reflects through itself and changes its polarity on the outer edge. So once again, there's no time domain model as to how this actually occurs inside of the chem field, but if we just apply the conservation of energy, we can say that we can just cut this chem field up into different components that can correspond to different aspects of this interaction. We can emit a photon, which is this red. We can have continued oscillation, as the electron might not just stop and emit all its energy all at once. And we can have recoil. So we know in the standard model that things will actually bounce backward when they emit a photon. So that's what this is. Have a nice night, Darby.
Sorry, I have to run.
Sorry.
Thank you.
You're welcome. So that can essentially look like this. So if the photon is traveling upward, it can emit a photon and continue going that way, where we say its deacceleration has corresponded to emission, which is once again different from the normal interpretation of Maxwell's equations, where we say an acceleration creates the electromagnetic field. We say specifically it has to be a deacceleration in order to conserve energy. And then we have recoil off of the emission process. Now, what I previously showed was a special case where we had an even number of rows, so it was very easy to chop this quanta into a photon and other stuff. But we can also have, obviously, the odd-numbered case where it's not so easy. What we can do is we could potentially emit multiple photons. And this could potentially be related, but I haven't done it yet, to the idea of the creation of entangled particles, where once again, the first explanation for entanglement that we have is that there actually is no instantaneous information transfer between the created particles. What has happened that as a result of their creation process, they were created symmetrically. So they just automatically were created with spins in the opposite direction or polarizations in the opposite direction. And that nothing has actually happened when we create a measurement and then immediately infer that this other measurement must be true. So we can still conserve momentum by creating multiple photons if we have them emitted at a specific angle. So in this case, we just say if it's 60 degrees, the cosine into the horizontal direction is 1/2. So we have still a cancellation of momentum, as well as then continued oscillation. So I've drawn these as red, but these should be the opposite polarization since we're traveling down. So this allows us to essentially describe in kind of a heuristic, geometric fashion the idea of we can solve a differential equation for some kind of perturbation or some kind of non-zero initial condition where it's just going to oscillate in some kind of curve envelope back down to zero. And these different maximums can correspond to emission. But now we're left with the question, once again, why do these measurements appear curved? Why do these triangles only approximate the exponential? Well, we can show that we can get a better approximation by including time dilation. So like I said before, we can say that in general, a photon or an electromagnetic wave should be made out of many, many different photons. So that's what essentially all these vertical lines are. There's a photon of, say, upward polarization and a photon of downward polarization. And we know that, once again, every interaction is subject to time dilation because these geometries rotate. We only create maximum force when they overlap in the same plane. So not just the same place, but the same time. So as a result of that, we could essentially have a linear change in amplitude, but if we space it non-linearly, because these processes can only occur at different sort of like time increments as a result of the change in energy or the energy content of this geometry, we get something that looks more curved. So that is nicer. And essentially, That's what I'm saying is occurring when we're measuring things, say like on an oscilloscope, is that if we essentially take this amplitude and we sort of extend it outward in time, because the different measurement processes and energy transfer in terms of our equipment and measurement devices takes a finite amount of time no matter how fast it occurs. It sort of smooths this all out and we get nice curvy measurements and graphs of things. So once again, this gives us the result that when we measure the frequency of some kind of wave, what we're measuring is the frequency of the source. So the source is going to emit and absorb at some kind of fundamental frequency or resonant frequency, which is what we get in the actual waveform. Then we say that these photons, when we talk about they have a certain energy content per frequency, that's talking about their actual frequency components, and that this is something else. So once again, we can remember that for a chem field, every unit of frequency is one repeating diamond geometry, and so we can have this distribution where right now, once again, we're just going to ignore these fractional frequencies because I basically just don't know what to do with them. And we can have, say, 1F, 2F, 2F, 1F across the triangle. For a photon, we can have a different distribution, slightly different, because it's more symmetric. We get a nicer distribution. And then once again, we can see that if we have some kind of forcing function where we're not just starting with some initial condition that is non-zero, we continually give the system energy at its resonant frequency, it will continue to emit or continue to oscillate. And we'll get this emission of this wave. Now, waves in general, whether we're talking about mechanical waves, vibrational waves, or electric field waves, electromagnetic waves, they're typically described with imaginary numbers. So essentially, as far as we know so far, it's kind of just a gigantic coincidence that imaginary numbers are so good at describing waves, even in Tetryonics. It worked out that way that the algebra works. But what is different in Tetryonics is that typically in the standard model we say the imaginary component of a wave, it doesn't actually exist. Like this is just a trick of the math that we're using to understand it. But in Tetryonics we see that when we saw the electrostatic field, it had magnetic components that were canceled. So in Tetryonics we say the imaginary component, it is a real thing, it exists, and basically it's the glue that is holding this wave together, this standing wave structure or this propagating wave. Now, in general, the imaginary component is just whatever is currently out of phase with the real part. So we could essentially say that the imaginary component is anything. We could describe it as the magnetic component, or we could describe it as the electric component. It depends on how we're trying to couple with this wave in terms of measuring it or creating it, or what we're essentially trying to work with. So we could essentially create an antenna that is a dipolar antenna that can create electromagnetic waves out of the acceleration of charges, or we could create a magnetic antenna. Now, a magnetic antenna is a real thing. It actually exists in engineering. They're typically not used because they're very inefficient. Because once again, we've seen that the magnetic field is a lot weaker than the electric field. But once again, in general, this imaginary component can describe whatever is out of phase with what we're trying to work with. In terms of a vibrational wave or a fluid flow of some kind, we could say that a high pressure precedes a flow. Or we could say vice versa, that a flow is going to precede some kind of compression, which is going to create a high pressure. So in general, we can have this imaginary component describe almost anything. So in terms of conduction current, this produces something very weird and interesting, where we said before we can have longitudinal electromagnetic waves pass through a conductor. We can also have conduction current pass through a conductor. So what we end up with is we end up with two orthogonal systems with two different orthogonal components in terms of the wave function. So we can have the electric field, and then out of phase with that is the magnetic field, and then say this transverse this longitudinal electromagnetic wave could knock an electron free and create conduction and voltage. Or once again, we say voltage is out of phase with current. So we have these two different systems where energy can transfer between them, and they have two different orthogonal components. So essentially we could describe any system in the most general sense that I can think of as we have a real and imaginary component in two different systems, where we can have an exponential growth in one system, which can correspond to an increase in the amplitude of these different components. And we can have, or this is an exponential decay in one system and an exponential growth in another. So we essentially have cos and sine, which are out of phase with each other, and they each have real and imaginary components. And then we essentially have, like I said, exponential growth and decay terms in both systems potentially through time and space throughout the system. So we can also connect this idea of the discrete frequency components of a wave, being the frequency components of these photons and chem fields, to the mathematical field of Fourier analysis. So normally we can describe any function as being the superposition of essentially an infinite number of wave functions with different weights depending upon their frequency. So if this is true, we can see why that must be if everything is constructed out of these energy components that have the same properties, but they've been tessellated differently. So what we can see is that positive frequencies can correspond to essentially one orientation of the geometries, or one polarization, which has been emitted from one specific type of deacceleration on one velocity direction. So we can say that, say, a velocity going up when it emits after it decelerates will create one polarization, and we can say that that's positive frequency. When it's going the opposite direction and it decelerates and emits, it will create a polarization going the opposite way. We can say this is negative frequency. And so we have this geometric description of the Fourier transform of some type of time signal. We also have the mathematical formula of convolution, where convolution usually describes the way that two different signals or a system will superposition, and what the resulting signal or the resulting response of a system that is receiving a signal will be. And basically what we do in convolution is that we overlap the two graphs. We flip one around and we give it some kind of delay, and then we change this delay between all different possible delay values so that we essentially raster this geometry over top of the other one, or the graph. In Tetryonics we can see that what we're literally doing is we're seeing how this geometry is going to superposition with another one as we move it across it, essentially. And that's going to give us the resulting superposition of this system, or these two signals. So what is kind of interesting is that we can also relate this to the idea in Fourier analysis, where if we give a signal a time delay, this is going to correspond to a phase delay in the frequency domain. So if we're going to have one chem field interact with another, instead of releasing it at one time, we're going to wait a while and release it later. So what's going to happen is that the receiving chem field is going to go through its intrinsic rotation, so that by the time our released chem field gets there, it's going to overlap in to a different degree in our reference plane. So we're saying our reference plane is whatever geometry we are measuring with is. We can also use this to get a kind of geometric description of what an impulse response is. So normally when we're characterizing systems in terms of their frequency responses to different signals, we give it an impulse response, and we can say that the resulting response of a system with regards to any input signal is the convolution of the impulse response with that signal, I believe it is. I might be stating that or remembering that incorrectly, but that's the general idea. That an impulse response essentially gives us the span of all of the different frequency responses that this system can have. We can kind of think of it like it's describing all the different modes of vibration of this system. So in terms of Tetryonics, what we can describe that as is we're giving something that can ring a whack. We're essentially smacking it as hard as we can without breaking it, and then just seeing how the vibrations slowly die down in time. So we can essentially create an overlap with different magnitudes and different phase delays in order to recreate how the system might interact due to some signal coming into it. So now that we know how we can relate waves and all these different ways to Tetryonics, we can now go back to this math and describe an additional description for entanglement. So we said before that one possible description is just that things are created in a symmetric fashion as well as destroyed. So what we're going to see is that in Tetryonics, entanglement can actually be a multitude of different phenomena. Like I said before, in terms of creation of entangled particles, they're simply created symmetrically. If one electron comes out of this creation process spin up, the other one has to be spin down in order to conserve momentum. And so that's basically what's all that is going on with that. But in terms of, say, action at a distance and actual information transfer between two different particles or two different systems, how we're going to recreate that is through the idea that, once again, the wavelength of a photon or a chem field, or basically any field geometry, is not even close to its actual size. And what is occurring is that longitudinal electromagnetic waves can be created not just inside of a conductor, but also in free space, and that they can transfer information faster than the speed of light. So if we actually calculate how big a photon is, where this is the length across the diamond geometry, we can see that even for very small energies, it is huge. So this is 43 meters across for visible red. Kind of just sit and think about that for a second. That is gigantic. We can also describe the height of a chem field from its base to its tip. So for, once again, visible red, it's 54 meters. It's 54 meters big. So this is essentially how we connect Tetryonics to the idea, once again, of wave functions and probability densities describing particles. And also the idea that force is created by overlap. So technically we could say that right now we are probably touching the walls. We don't feel it because we haven't created enough overlap of our wave functions with them to create essentially a repulsive force that we can actually measure, we can actually feel. But it could actually be happening if Tetryonics is true. So you might be wondering, well, why don't we measure these fields so much easier then? Once again, we have a simple and a complicated example or answer, and the complicated one is that we actually do. So this is obviously a jet going supersonic, and what we can see here is this, forget what it's called, it's the sonic boom. And essentially what we can kind of infer from Tetryonics is that this is essentially the sonic jet's chem field. It's not the actual front of it, but it's where the overlap of this chem field with all the energy of motion of the air is big enough that it can compress them to the point that it's changing the refractive index of this air, and we essentially can't have light pass through it, and we actually see this puff of like cloud is what it looks like. This is also sort of related to the idea that we can't go faster than the speed of light because of diminishing returns. So in Tetryonics we see quantization when we try to work with things very small. We also see it when we work with things very big. That it becomes significant on both sort of ends of these spectrum of energy. So if chem fields are this gigantic, once again, we can explain the whole wave-particle duality of matter. So when we have, say, this double slit experiment, what physicists did is they have essentially a wall with two slots in it, and if you pass a wave through it like water or light, it's going to create an interference pattern on the back wall. As the wave passes through, then overlaps with itself and creates this interference pattern. So what they did is that once Schrödinger had his wave equation for describing particles, and they also had de Broglie's description of pilot waves, is that they did the same experiment with subatomic particles. So you take something that is radioactively decaying and you shoot it at this wall, and you say, well, some of the particles are going to pass through eventually, but they're going to pass through a random slit. But what they measured, once again, was an interference pattern on the back wall. So Tetryonics predicts this is a result of these particles' chem fields. The chem field, like we saw, for even a low energy is huge. So the chem field passes through both slits and interferes with itself, because it is a wave and produces this interference pattern. So once again, we see this idea that we do measure this effect, that these geometries are gigantic. One way that we could potentially test Tetryonics, which seems kind of ridiculous, is that if this is true, macroscopic objects should do the exact same thing, as long as we can measure it correctly. We fire cannonballs at a wall, and then we somehow don't have them impact on this back detector so that it destroys it. We should actually be able to measure their energies of motion and see that it creates an interference pattern, or even say like tennis balls or something like that. So the way that we create action at a distance is once again through longitudinal electromagnetic waves through free space. So what ends up happening with the longitudinal electromagnetic waves is that all of these linear momentums superposition in such a way that the resulting interaction can transfer energy across this geometry much faster than the speed of light. So this is predicted to be what actually happens in terms of electrical conduction and longitudinal electromagnetic waves in the material, is that there was actually an experiment, I forget how long ago, potentially more than 100 years ago, where Charles Wheatstone, I think his name was, the guy who made the Wheatstone Bridge, he actually measured the speed at which electrical energy travels through a circuit, and he actually measured it to go faster than the speed of light. Now, this wasn't thought to have very much significance because this is dependent upon the material properties. You can have it go much slower, you can have it go faster in some materials. And so people didn't pay much attention to it, but at Tetryonics we predict that it's because of these longitudinal electromagnetic waves that we have these different results. So we can see that these longitudinal electromagnetic waves are present in a lot of our geometries. So inside of electrostatic fields, we have them. Inside of photons, we also have them. So in terms of entanglement experiments, the reason why one measurement can affect another one very distant is because there is a longitudinal electromagnetic wave connecting them, and energy can pass through it faster than the speed of light. So what ends up happening is that in some of these experiments, we can't say that these measurements are separate or that these are separate events. It is one event, one measurement performed upon a composite system. So to describe sort of intuitively how this energy can transfer through this standing wave faster than the speed of light, we're going to use a physical example. If we essentially have a long cylindrical drum and we tap on the end very hard with a constant frequency, eventually we will create a standing wave inside of this drum consisting of nodes where we have inward velocity and I forget what these are called, but where there's outward. So this inward and outward velocity at different points that is changing in time. And say what we do is we hang a micro explosive right here or at one of these nodes. It doesn't really matter. And we time it so that it explodes right when, say, all of this velocity is coming in or all of this velocity is going out. Obviously, the explosion is going to create a pressure wave. It's going to create a longitudinal, excuse me, it's going to take a longitudinal wave. Because this is traveling much slower than the speed of light, we can assume that they're going to linearly superposition. So what we can describe is essentially this is going to send a pulse towards the ends faster than the speed of sound of the material. Once again, this is something that should actually be testable. We could actually try this. Tetryonics also predicts that it should travel faster the higher the frequency of this standing wave. So if we could actually demonstrate this, what we can essentially demonstrate is that we can have a macroscopic system display properties of an entangled system, where we can essentially say that this side is entangled with this side, basically. Potentially better way of describing this, and a more truer way, in my opinion, is that the pulse doesn't actually travel along the standing wave. It doesn't actually move. What it does is it pushes the energy at the edges outward. So we can, if I just go back here, we can think of this standing wave as a rigid structure, which is not entirely silly because we know that matter is a standing wave and it is definitely a rigid structure. So in the context of matter, if we have this Newton's cradle, what we do is we suddenly, this is all obviously completely hypothetical, we just magically have a ball appear right here. What's going to happen is it's going to push the side balls out the side. They're just going to pop out. So essentially we say that this is the way that energy is transferred through a longitudinal electromagnetic wave. This is actually pushing on the wave structure. And what we've essentially created is not a pulse that traversed through space and time, but we've essentially Doppler shifted the energy at the edges towards the blue. So we suddenly measure this piling up of these wave fronts at the edge. Like I said, what we've done is that the pulse doesn't actually travel from here to the edges. What it does is it pushes the wave structure into the edges. So what we've created once again is Doppler independent blue shift at these edges. So this is once again how action at a distance is working, how we actually transfer energy, say through a gravitational field or through a charge field in order to produce an acceleration. But where once again this is just kind of theoretical explanation, we don't actually have a model of this in time, of these actual quanta doing that. And so once again, this can happen in these different systems where they're trying to measure the influence of one particle state on another. It's not actually the particle, it's their actual measurement systems itself that are doing this. So Tetryonics predicts that we should essentially see a decrease in the successful amount of measurements if we just increase the distance of separation between the two different measurement sites. But obviously we have to increase the distance by a lot, because these chem fields, even at room temperature, are basically like 60 or 70 meters across. Now, the reason why I specifically said it should decrease the amount of successful measurements, not completely eliminate them, is because, as we've seen before, these longitudinal fields exist in electrostatic fields as well as in photons. And we know from yesterday that we're essentially in a gigantic electrostatic field due to our sun. So it might still happen, we don't actually know. So the potential for this action at a distance already exists everywhere around us. So if we wanted to create devices that can exploit it for communication or energy distribution, we might not actually have to artificially construct a standing wave structure. We could just do it. Now, there was one additional point I wanted to make. I'm just trying to remember. Nope, let's go on. Okay, so. All right, yeah. So one way that we might actually be able to do that, and this is another thing we could test, the way that we actually create this pulse that will hopefully travel through the standing wave structure, is let's say we have some already standing wave structure, like some big electrostatic field or something like that. We essentially just very quickly create a pulse with the same field orientation, like this, where this is a photon, and we create it so that its wavelength matches the wavelength of the wave that is already there. So that we get this maximal overlap, and it pushes on the wave structure, and hopefully creates a pulse out the sides that we can see. Now, you might be wondering that if all these fields are absolutely gigantic, why does light and things like that work the way that we already know that they do? Once again, this comes back to the idea that all of the fields are very large. So chem fields are large, photons are large. It's unclear to me whether or not matter should be large. Kelvin says that it isn't, that these are all actually very, very tiny. But if we think about it, once again, it doesn't really matter what size they actually are, because force is created by overlap. In order to create some kind of interaction, we need some critical level of overlap, and essentially we need to have it offset in a certain direction. So say, in terms of some kind of semiconductor or glass plate, we know that because it's potentially polar for glass, or the electrons have some kind of orientation due to the material's crystal structure, its static field or standing wave is going to have preferential orientations for reflection and absorption, which is something that we already see, basically. If you have light go into a pane of glass, it has a refractive index where it's going to shift the direction that the light is moving by so much, depending upon the incoming angle. So once again, we know that obviously light actually does that if we have a prism, we can separate it into its different components, where once again, due to electromagnetic wavelength contraction, these have a certain size and energy density, so that when they overlap, it creates a varying amount of force on them. So it won't push on violet as much as it pushes on red, because violet pushes back very strongly. So as a result, violet isn't diffracted as much. Whereas, or I think it's the opposite way around, actually. Anyways, there's varying amounts of interaction on each one of the wavelengths due to its energy content. So, hopefully, by now we have essentially justified all of our initial assumptions that we had about energy, except for its actual geometry itself. Once again, like we were talking about during the last lecture, we have no reason to pick triangles other than that they create the standard normal distribution. But in terms of their actual electric and magnetic field components, there is no reason to have that. We just tried it and it worked. Same thing with tetrahedrons. We tried it and it made all this cool stuff. So we're left with essentially only two assumptions that have no justification so far. That first one is the Lorentz invariance of matter. So we said that the standing wave structure of matter doesn't actually change when you make matter go fast. What changes is the chem field. And once again, there's basically no reason for that. We don't have a reason for it. Well, once again, as far as I know, it wouldn't actually change anything if it did. It might, not exactly sure. So for now, we just say that it doesn't. The second thing is the wavelength contraction of energy itself. We essentially have no justification for that. It's something that we just measure. And once again, there's nothing stopping us from saying that it's true. We can't not do it in terms of the rules that we've defined. So we arbitrarily say that this is what happens. So our final two topics are the inverse squared relationship of electric fields. And once again, we're going to talk about, we talked about time continuity before, how things can become curved due to time dilation. We're going to talk very, very briefly, obviously one slide, about spatial continuity. So in terms of the inverse squared relationship, we can essentially create a two-dimensional electric field, where normally they're described as being spherical. So here we're going to say that it's a circle. And at the edge of this circle, we say that this circle's edge is where we essentially measure no electric field. Like it's basically arbitrarily close to zero. We can call this, say, the minimum potential enclosure of our charge at the center. Through the two-dimensional Gauss-Bonnet theorem, we can say that circle has the same total curvature as a diamond. So here we're just showing 1/2 of the diamond. We can say that for so much circular area, we have a triangular area or a diamond area. Now there are mathematical equations that I don't have on here, but you can very easily solve for the total area of overlap between these two different minimum potential enclosures. And then you can correspondingly convert it into a triangular overlap. So in two dimensions, we say here that the voltage, say, of a charge, which say is the blue, which we're measuring relative to our test charge, which is the white, is inversely proportional to 1 over r. In differential geometry, we have this idea that 1 over r is curvature. So we can see that what is going on is that we could essentially more generally define voltage in electric fields in terms of inverse curvature and say that this is equivalent to inverse distance. Now the reason why we would want to do that will become more apparent when we see this in 3D. So once again, this is just the idea of the Gauss-Bonnet theorem that for every circle we can have a diamond inside of it. But in 3 dimensions, we saw for the 3-dimensional Gauss-Bonnet theorem that we can have coordinates of curvature on these two different perpendicular circles, that we can create all the points on a circle out of these different essentially angles along this circle. So in 3 dimensions, we can say that we have 2 different perpendicular axes of curvature that are overlapping. So this is what creates I think so far, this is as far as I've gotten with it, the inverse squared relationship for voltage in 3 dimensions. So we saw that electrostatic fields are, they're essentially like 2 perpendicular cones. And you might remember from the first lecture, we said that we couldn't describe an electric field as being this 2D geometry rotated, because that would require an infinite number of planes, which says that electrostatic fields have an infinite energy. So we're predicting that they are likely actually cone-shaped. But once again, through the Gauss-Bonnet theorem, we're still going to create the same interaction, because this shouldn't actually be distance, it should be curvature. And once again, force is created by overlap. So you might wonder, well, why don't we measure this electric field way out here at the points? We come back to the same idea that because force is created out of overlap, there just isn't enough overlap there that we can create a measurable change in energy, even though potentially the electrostatic field is huge. I haven't performed a calculation for calculating how big an electrostatic field is, like I did for chem fields and photons, because I'm not yet sure how I should calculate its energy, because that's how we have to arrive at the size of it, is we have so much wavelength basically per energy and things like that. So I just don't know how to do that for an electrostatic field or a magnetostatic field. That is how we get the inverse squared relationship. Wait, that's the wrong direction. Okay. So now we're left with the one final question we'll try to answer tonight, and that is, why don't we measure, how do we measure continuous distributions out of discrete objects? So this is not really obviously a problem that Tetryonics uniquely solves or anything like that. This is actually fairly intuitive if you have ever studied the mathematical field of real analysis, but now we can combine it with the law of uncertainty in Tetryonics. So we're not going to go into this basically at all. What I've done is I've taken essentially a basic theorem from real analysis describing the limit of a sequence. We basically say that if we have a sequence of numbers, we can say that it converges to a limit if we have, for any epsilon greater than 0, we can choose some type of n, where n is some point in this sequence. As a, what should we call it? This n is a function of epsilon, such that if we take this an for all n greater than this n that we've chosen as a result of epsilon, and show that the difference between the elements of this sequence and its limit is less than epsilon. So basically, in a nutshell, what we're saying is that this sequence converges to L if its elements can get arbitrarily close to L. So the distance between them will essentially go so small that we can pick any small number greater than 0, and it's still smaller than that. So what we can do in terms of real analysis is that we can use the idea of something called an open ball. So we have some circle of some radius, and inside of this circle maybe we have other circles, other open balls. And we can start to describe this idea of like spatial limits and other things like, I forget, it's been a while since I've read about this, but basically we can say that if we have a bunch of stuff packed really close together, essentially it becomes continuous. We say that it's the actual definition of continuous if it is arbitrarily closely packed together. But once again, we can see that in Tetryonics, we can arrive at this result faster because all of our measurements are subject to uncertainty. There are always some kind of mismatch or fuzziness to them. So that is it for this final lecture in Tetryonics. I hope you all enjoyed yourselves, and I want to emphasize very clearly that the majority of all this work was made by Kelvin Abraham, and it is essentially only through his heroic effort that most of this even exists. So some of this lecture was a lot of my work that, once again, Kelvin disagrees with. It's not necessarily canon to normal Tetrayonic theory, but Kelvin has basically worked on this theory for about the past 10 years and basically not gotten very much positive encouragement or recognition at all. So maybe you might want to thank him if you enjoyed yourselves and are interested in more information about the theory. So once again, he has a YouTube channel with essentially more than 100 hours worth of lectures on this theory on there. He has published 5 ebooks on the Tetronic Google Plus webpage that are available for free. And all the stuff that we've seen over these lectures is only a small fraction of all the things that he has created. So we barely even got into chemistry. We didn't talk about molecules or intermolecular bonds and things like that, which is all stuff that he has done, as well as more things on cosmology, as well as even music, stuff like that. It's very interesting. So I want to now see if anyone has any questions, and then if people want to, we can talk about further things that are essentially, they're just fun, essentially. How we can kind of imagine how Tetryonics might change the world for the better as a result of it creating new and interesting technologies. So is there any questions? Nope. Do you want to see other things that I've thought about?
Sure.
Okay. So the first is we have essentially a completely deterministic model of the subatomic world. And we said that while we have uncertainty, this does not equate to randomness. So we're kind of left with this interesting question that I don't actually have an answer for, but it's kind of interesting to think about, is that does probability and even free will, does it even exist? So this is one potential interesting question that philosophers have probably already thought about a lot, is does free will even exist? So I have this quote from Immanuel Kant, where basically, Soren Kierkegaard, basically my interpretation of this is that it doesn't even really matter whether or not free will exists, because the illusion of it is very real. Like, I don't think anyone could have predicted that I was about to do that. So yeah, I say it doesn't really matter. At the end of the day, we're still going to choose what we're going to choose and justify it however we want to justify it. Now, what is very interesting is if Tetryonics is proven to be right, is that it essentially forces us to ask a question: does science as an institution even work? So normally we think that science, not all of the effective knowledge rises to the top, and that over time it averages out and all the good ideas get their day in the sun. But what is interesting is that obviously Tetryonics, it flies in the face of, like I said, 70 years worth of particle physics and quantum mechanics. So as a result, a lot of people really dislike it. Even if it has merit, they don't want anything to do with it, essentially. They don't want it to be true. And so what's interesting is that it shows that you could potentially be in a conflict of interest with regards to weighing in on your opinion about the validity of a theory as a result of your own expertise. So even though you are the best person qualified to say whether or not it's true, your opinion might not be trustworthy. If, say, what it does is it proves embarrassing for you or something like that. Like I was talking about before, the Large Hadron Collider, if this is all true, is potentially a $10 billion hole in the ground. But then who do we ask, instead of particle physicists and theoretical physicists, whether or not this is true? So we have this strange ethical dilemma that even though science doesn't fail often, when it does fail, or if it does fail, it will fail catastrophically. And so these are essentially different ideas that I've actually sort of borrowed or stolen from TED Talks. That the idea that scientific theories, like I was talking about in the first lecture, they cannot be proven through observation. Science is not necessarily truth. It's probably better described as knowledge that is effective or useful because it allows us to make predictions and do cool things or useful things. And we say that we can only disprove a theory through observation because we can never essentially know perfectly whether or not the effects we observe due to an input are in a causal relationship with that input or a correlative relationship with that input. And then once again, we have this very cool idea that someone was talking about in a TED Talk, that An explanation is good if every detail of it is functional, that there are no arbitrary components. We eventually say that like a good theory is like a very well balanced house of cards, and that if any point of it fails, the entire system should fail, at which point we start over. Now obviously if this theory is true, and we can actually create time domain models of how energy is transferred, we can apply this to chemistry. We can do essentially now all sorts of amazing things in terms of designing molecules, potentially even genetic engineering, creating drugs and materials and things like that. Where once again, what could potentially happen very, very distant in the future is we could design organisms essentially from scratch to do a specific job. So you could essentially create an organism that just eats one material and gives you a material that you want. It's very amazing and interesting. Another thing is that already we can basically already see the way that we could create an artificial gem pinch. We saw before with those plasma circulations, we can essentially just replace that with loops of current, and as long as we can optimize it correctly, that we have the correct material with the right current density to create the maximum amount of electric and magnetic flux that is going to start to tear matter apart without breaking our device, we essentially have an unlimited supply of clean energy. And we can use this for all kinds of amazing things. First, that I sort of envision is we could use it to vaporize large quantities of seawater. We take the water vapor and we use it to turn a steam engine, which creates electricity. Once the water has been completely exhausted of all of its potential energy, we condense it, we have purified water. So you could essentially imagine that we could essentially end drought everywhere throughout the world, as well as make farming possible basically anywhere, as long as water was the only thing stopping it from happening. Now what is also amazing is that there is this book by a guy named Takashi Yabe, where essentially it's called the Magnesium Civilization. And the idea is that you could use magnesium as fuel inside of a specific type of fuel cell. Now, the ocean is estimated to have something like 70 trillion tons of magnesium in it. And what is great about magnesium is that even though now it's super expensive and this process is too difficult and it's not economical to do, or to just say like refine magnesium out of the ocean, so that it was really cheap, we could create magnesium fuel cells. Well, what is even better is that the magnesium oxide that is produced can be separated back into magnesium and oxygen, so that we can essentially recycle our own fuel that we have created. And we can create a closed loop energy cycle where there is no longer any pollution or waste. What is also interesting about gem pinches is that this allows us to do that potentially even for carbon dioxide. So even if we switch to a new fuel source, we still have the problem of global warming. Even if we stopped burning fossil fuels today, the amount of carbon dioxide that is already in the atmosphere would continue to cause our planet to warm for a long time to come. But with applying all the huge amount of energy that we get out of a gem pinch to high energy chemistry, we can essentially reduce carbon out of carbon dioxide and transform it into useful new compounds like carbon monoxide, which can be reacted, I forget with what, with some like hydrogen or water or something to create methane, or I forget exactly what it's creating, because once again, I'm not a chemist, but there's different processes, like pyrolysis and pyrolytics, where you can essentially convert carbon dioxide with a huge amount of input energy, because it's stable, back into other things that you can then transform into, once again, fossil fuels and burn again. So with the use of a gem pinch, we can do all sorts of amazing and interesting things. We also have this idea that we can travel to other star systems. And basically, like I said during the first lecture, is that in terms of economic reasons, this makes war pointless. There's essentially no reason to fight over any resource or energy sources because the universe is essentially filled with an infinite amount of both of those. All you have to do is go out and find it. But once again, this doesn't necessarily stop people who are insane from doing crazy things. So that is something that you still have to watch out for. And that is the complete and have everything that I have constructed so far out of the theory of Tetryonics. But once again, this idea of three-dimensional quanta is essentially my own idea. And the rest of it is basically all Kelvin's. Thank you for coming.